So yeah. So if we go on to our okay, let me just start from the presentation. Um, so we have a midterm coming up. Um, on our syllabus, we said that the midterm would be on July 17th. I think it would probably be better. So like if we look at the calendar, right? July 17th would be a week from today. I'm proposing that we push it forward to the 22nd so that instead of having it on that Wednesday, you have it the following Monday, which would mean that we would finish the material for the exam on Wednesday, and then you would have that weekend plus you would have the rest of that week and that weekend to study and prepare for it. I think that would be my preference because it would give you more time to study, but also because this class is a little bit, it's 10 minutes shorter than the way the class was last year. So I was kind of basing the timing on how many lectures I got through last year, but since every lecture is 10 minutes less, I'm effectively short one lecture if we make it at the same time. So I could get through everything I was planning to test you on by the 17th, and then we could have the exam on the 22nd. That would be my proposal. If there's any issues with that, let me know. Like if you yeah, if there's any issues with that time, let me know. But I assume that that's probably preferable. And so the exam will be in class on the 22nd. We'll use the full class time. It will be no notes, no calculator, closed book. There is a review, and there's a couple things to take a look at on our Google Drive. So if we go into our Google Drive under exam materials, that's where you can find the study guide. And so this study guide is updated based on the date that we will have it for this semester. Um, in terms of what the exam will look like, there's going to be four parts. You'll have some multiple choice questions and some concept questions where you give like a written answer. So those two first parts of the exam will be kind of like on the problem set, you've got the questions and then you've got the problems. So the first half of the exam will be kind of like those questions. And then the second half will be like the problems where you have some kind of combination of numerical problems or derivations. Um, so in general, what will be covered is based on what is in the full scope of the exam is based on the notes. Anything that you see in the notes could appear on the exam, but in terms of like a starting point, reviewing the practice problems and understanding the practice problems, the quizzes, the in-class examples, the in-class derivations, you will find that if you are comfortable with the problems on the problem set, when you come to the exam, there's going to be no surprises. It should be relatively straightforward. So that's always my advice is to make sure that you are giving those problems sets the practice, spending the time on that practice so that you are building the skills that you would need to be successful on the exam. Um, and yeah, that's going to cover most of what you would see. And it's going to stop at problem set three. So the material will be chapters. If you're looking in Svekov's notes, it's going from chapter 0 to chapter 4. We're going to get through as much of chapter 4 as we can. And that's mostly defined. Yeah, we'll pretty much be stopping where problem set 3 stops. Um, and there will not be a new, well, next Wednesday, there will not be a new problem set. So because next Wednesday, yeah, will be the last day that I talk about what you would need for the third problem set. And so going through this, it just kind of explains the kind of policy for the exam. There is a formula sheet, and that's also on the Google Drive. So it's going to cover the first four chapters following Dr. Svedkov's notes. So chapter 0, chapter 1. We are currently in chapter 3, which is all about one group diffusion theory. And then we're going to get through as much of chapter 4 next week as we can, and then that will be also on the exam. And so if you go through this review, it kind of tells you about all of the different items that you should be aware of and what pages you can find that information in Dr. Svedkov's notes. I would highly recommend going through this point by point, making sure that you understand these things, and if there's any derivations derivations stated here, make sure that you could do those because any derivations that are mentioned here could show up on the exam. And so this basically just goes through the different concepts of the different chapters that we have or will talk about. And then at the end, there's a list of study questions that covers like the main topics and concepts that we will see on exam one. So you'll find that these study questions are very similar to the questions part of the problem sets. And then so this would be a good kind of way to review those things. And then in terms of the problems, doing the problem sets, and understanding the quiz questions as well, would be the way to go. So if I was in this class and I was trying to prepare for this exam, I would make sure that I did all the problem sets, that I understood my quizzes, and then if I missed anything, I made my corrections so that I wouldn't make those same mistakes on the exam. And then I would spend as much time as I can going through this in detail and reviewing the individual points, so that I make sure that I've seen and practiced everything that I could see so that there's less chance of there being a surprise on the exam. So that guide is there for you. This is the formula sheet that you will see on the exam. So the exam will be like a booklet, and then this will be the last page in the exam. You can like tear it out when the exam starts, and you can have it next to you. Not every formula that's on here will be needed on the exam. So it's important to be able to recognize these formulas from what we've talked about in class. This drastically reduces how much you have to memorize because you don't have to memorize every single form of every single equation. But so, like, if I was in this class, I would print this out and then I would make my own version of it where I'm describing what each of these things are. That way, you're not going to be able to probably do that on the exam itself. But if you've studied the formula sheet and you know what formulas correspond to what kinds of problems, then you're going to be at a good. Worst thing that you could possibly do is not look at this until you have the exam, because then you're going to be looking through a bunch of stuff and trying to find things, and you do not want to be spending time trying to look for the right formulas during the exam. You want to be comfortable with this. Like I would print this out today and I would use it while I'm studying for problem set three and also while I'm studying for the other problem sets too, if I haven't done them yet or if I'm practicing them, so that I can be like, oh, okay, here's the formula for the power density that I'm going to use on this problem. Now I don't have to memorize it. I just have to remember that that's there if I need it. And same thing with any of these other definitions or governing equations. So these are all like big formulas. And then on the back side, you've got some other information that is possibly useful. For example, this is the table of all of your fundamental mode flux shapes and the geometric bucklings. So it's not labeled, but you would want to be able to know that this is there. You would want to know which equations correspond to which geometries. Since I'm not providing that information for you, so we should know like this is an infinite slab, this is a rectangular parallel pipe bed, this is a 1D cylinder. This is a 2D cylinder. This is a sphere. If so also your definitions for the gradient operator, for the divergence operator, and for the Laplacian operator are here. So you don't have to memorize what those are, but you need to know which corresponds to which geometry depending on what problem you have. And then this is another table that's very useful so that if you have some governing differential equation, you can jump to what the general form of that is. We kind of talked about that last time, and we'll get an example today where we practice this a little bit more. This is a very useful thing to have so that you know which equations, what the general forms are for different equations that you might end up with, like for a derivation, for example. So yeah, this is there for you. You will see this on the exam. If you have any questions about this or the review or about anything else, definitely don't hesitate to ask. And then, yeah, I guess the only other thing is that you just got the problem set, but also if you need an extra copy of the problem set, you can always find those and the previous two problem sets in our Google Drive as well under suggested practice. Um, any questions about the exam or the review or anything so far? All right. So if there's no questions about that, then we can get into our topic for today, which again was multi-region diffusion. So when we talk about a multi-region system, we should just generally be aware that real reactors are multi-region systems. So this picture right here is the picture of like a full PWR reactor core, which contains lots of different kinds of materials. And this picture, like on the far right, is a picture of a fuel assembly. Within a reactor core, the fuel is in these giant assemblies that are placed inside of the core. They can be lifted out and rearranged within the core. And then the fuel assembly is made up of these individual fuel elements. So, like the fuel is the thing that makes everything go. That's going to be traditionally, you have in our reactors these little pellets, which are like usually a uranium dioxide pellet. That uranium would have like a certain U-235 enrichment, and that's your fissionable material that is used to make your chain reaction happen. Um, you take a bunch of these fuel pellets and you stack them on top of each other. You put them in a metal casing called cladding, and you add some springs and some insulation to make sure that those things are like staying compressed next to each other. And then that makes up a fuel element. Um, and the fuel assembly is just a collection of fuel elements, as well as there's different channels in those fuel assemblies to allow for like a coolant to pass through. The coolant is what's going to be used to remove the heat from the reactor core and transfer it somewhere else, hopefully to produce power. But also, you might have like a research reactor that's taking that heat away and not using it for like maybe a useful purpose, but you're just making sure that you have some way to cool that reactor down because reactors can get very hot. If you are, most reactors that we deal with are thermal spectrum reactors, which means that you need a moderator to slow the neutrons down. Um, we'll talk more about that when we get into energy dependence in chapter 4. And then you have control rods, which are some kind of very good absorbing material, so that if you need to shut the reaction down, you drop the control rods into the reactor core. It absorbs a lot of the neutrons and takes you from a critical configuration to a subcritical configuration where your chain reaction can no longer continue. And then real reactors will also have reflectors. These will be like kind of good scattering materials that are placed on the outside of the core. This helps to prevent neutrons from leaking out, but it also allows any neutron that might leak out of the core to hopefully scatter back in and be used to make another fission happen. And then they will also involve shielding both around the core itself and in like the giant containment dome. Those shielding materials are used mostly to protect the public and also workers at these plants from the high radiation fields that are coming off of these reactors, because these reactors will produce a lot of gamma rays and a lot of neutrons, and some of those particles will leak out. And if you don't have something to stop those materials, then it gets stopped by a person, and that's not good. Um, so yeah, that's kind of justifying why we have a multi-region model for a reactor. And right now, we're just kind of thinking about multi-region problems in a way more simplified way. And so that was kind of how we're going to start. This right here is the diffusion equation, the one group diffusion equation, and we're writing it for just any region I in our reactor. And I had to redo my slides, so if you printed these out, I had superscript i's on all of these material properties too, because in every region, you might have different materials from one region to another. We're going to assume that within a given region, all of the properties within that region are the same. So like the diffusion coefficient, the absorption cross-section, the nu F and the sigma F are generally lumped together. So you can just kind of lump that whole term together as saying, I have this value of nu F times sigma F for this region. And within a region, those properties will be the same. But if you go from one region to another, like if you go from fuel to a reflector, then those properties will change. So the superscript I just helps remind us that this is an equation for one particular region. And if we have 5 different regions, then we would have 5 of these equations that describe what the scalar flux is doing in each of those regions. At the outer boundary, we are still going to keep assuming a vacuum boundary condition, which means that at the extrapolated dimensions of the reactor and at all times t, the flux is equal to 0. And then if it's a time-dependent problem, then we need an initial condition. We basically need to know at time 0, what is the shape of my scalar flux. And so that's kind of the main stuff that we talked about for a general um, one region problem. But if you have multiple regions, then you have an interface where you go from one material to another. And if we want this scalar flux to describe what's happening through the entire reactor, the flux is a continuous function, which means that if we want the solution in one region to make sense with the solution in another region, we need interface conditions, which will match the flux at the boundary. At the interface, we need the scalar flux to be continuous. So that means that like if it's a two region problem, then the flux in region one at that interface location, so I'll say at our interface, and at all times t, it has to be equal to the flux of the other material. So at that interface, the flux in the next region at that interface has to be the same. They have to match. We got to match what the flux is at that interface. Otherwise, the scalar flux won't be continuous. So this is one of our interface conditions. It makes sure that we have continuity of the scalar flux, which makes sure that that value matches. But the other thing that we need to make sure matches is the current, which kind of relates to the slope of that function, the slope of the scalar flux. So we also have continuity of the normal component of the current. And to get the normal component of the current, you take J. So we'll say J for region one. And this is the current at our interface and at all times t. If we take that and we dot it with the normal vector at that surface, at that interface surface, that's the normal component of the current in region one. And that normal component in region one has to match with the normal component in the region that it's touching. So we'll say that has to be equal to the current in region two at that interface at all times t, and that has to be dotted with the normal surface vector at that interface. So, and technically, that's basically what we want to say about continuity of the current. Um, and when we are doing one group diffusion, we have made an assumption about this current that it is that if we think about Fick's law, it means that that current J is equal to minus D times the gradient of the flux. That's the definition of Fick's law that we've been using to get this one group diffusion equation. So if we write this in terms of Fick's law, then what we have, and I'm going to write it like this, I'll have the diffusion coefficient for region one, which I'm going to be able to pull out of any operators because we're assuming constant material properties within the region. And that's going to be multiplied by that normal vector at the interface and the gradient of the flux in that first region. So that's what my net current, that's what the normal component of my current would look like for region one if I use like a Fick's law approximation. And oh, and then this, I can include my arguments that this is at the interface and at all times t. Sorry about that. And then that's going to be equal to the current we have in region two, which is going to look very similar. I'll have the diffusion coefficient in region two times that outward unit normal at that interface multiplied by the gradient of the flux in region two. And this has to hold for all positions along the interface and for all times t. So that's the way that we could write the normal component of the current in terms of a Fick's law. And so we need boundary conditions, we need initial conditions, interface conditions, and we also, it's good to keep in mind our physical realizability condition, which basically just says the flux can be zero, but it can't be less than zero. It can never be negative, and the flux cannot go up to infinity. So this is everything that we would need to pose to solve a multi-region diffusion problem. And once we know what the kind of problem is, then we can start spelling out what our equations look like, what our operators look like, and then we can start moving through the problem-solving process. So I wanted us to start here, and then I wanted to use these things to do a example where we find the flux distribution in a multi-region problem. So kind of the simplest multi-region problem that we could start with is a two-region reactor where we have a core region. That's this inner red region. This would be our core. And that core is going to be made of like some kind of fissionable material like uranium-235. And then that core region is going to be surrounded by an infinite reflector. And that reflector is going to be made of some non-fissioning material, like maybe it's carbon or maybe it's yeah, iron or some kind of metal. So that's the reflector. And we're assuming it's an infinite reflector, which means that it goes from this interface location all the way to infinity. So if we want to solve a multi-region problem, what we need to do is first just start writing out the diffusion equation for each region. So this would be my diffusion equation for region one, and this is a steady problem. So if we think about the diffusion equation, like this guy right here, if it's a steady problem, if we're in steady state, that means the flux doesn't depend on time. And so if the flux doesn't depend on time or the flux is constant with time, then if I could take a derivative of that flux with respect to time, I get zero. So that's the only thing that simplifies if it's a steady problem is that this time derivative goes away. So that's basically what this equation is. I've just taken out that time derivative term because it's a steady problem, and then I've moved everything to one side, and that I've kind of lumped all of these coefficient or all of these constants together. And this right here, these terms lumped together, that is another, we defined a quantity based on these terms. Do you all remember what this quantity is equal to? Yeah, the material buckling. So that thing in the brackets, that's my BM squared, and I'm gonna write for region one. So inside the parentheses, that's just my region identifier, and then this two is a power of two. So that's what I have for this right here is my equation for region one. And if I want to write an equation for the reflector, it's going to look very similar to this. I'm going to write the diffusion equation for the second region. So it's going to look like the Laplacian of my flux in region two plus that term. But if it's a reflector, what's sigma f for a reflector? It's zero, right? The reflector can't fission. It's going to be made of some non-fissioning material. So this term right here is just going to be negative sigma A for region two divided by the diffusion coefficient for region two. And that's multiplied by V2 as a function of position, and it's equal to zero. And this equation, just like this is the region over which my first material is defined. The second material goes from the interface radius all the way to infinity. So we would say from interface radius less than r less than infinity. And because we want to write these equations in a similar form, and because we effectively have this now a minus sign up front, we call this term sigma A over D, we call that B effective. So we can simplify our reflector region to say that we've got the Laplacian of the flux in region 2 minus this B effective for region 2 squared, and that's multiplying the flux, and it's equal to 0. So that's my region one equation simplified. That's my region two equation simplified. And if it's a non-producing region, like a reflector or an absorber, then we would use beta effective instead of the material buckling. So now that we know what our equations look like, all we really need to do to move forward is we need to spell out what that Laplacian operator looks like for the given coordinate system. And in this case, it's a spherical problem. So it's going to look like the Laplacian for a sphere. Um, and then also we kind of want to think about our interface conditions too. So if it's a two-region problem, then we only have one interface, right? This right here is our interface. So at that interface, we need to make sure that the flux in region 2 matches the flux in region 1. So what we're going to say is that the flux in region 1 evaluated at that interface at R int has to be equal to the flux in region 2 evaluated at that interface. That's what our, yeah, that's continuity of the flux. And then continuity of the current, when we wrote continuity of the current, we had that gradient operator. Do y'all know what the gradient of phi looks like if we're in radial coordinates? If it was in Cartesian coordinates, like if we just had a phi of x, what would that gradient look like? Yeah, perfect. It would just be d phi dx and then multiplied by like a unit vector in the x direction. And so in our case, we have a 1D radial problem. So in a 1D radial problem, it actually looks basically the same. It's d phi dr, but then we're dotting it with a e hat r. And that e hat r just represents, in this case, e hat r is a vector. It's a unit vector that points radially outward from the center of the circle. And that e hat r is also the unit vector at our interface. And when we, oh yeah, oh, it's spherical. Yeah, 1D, it was a concentric spheres. So yeah, we're looking at kind of like a cross section of the sphere. Yeah, we're not looking on top of the cylinder. So it's like a nested sphere inside of a giant infinite sphere. So because of our radial vector pointing outward, and that is also going to point in the same direction as that interface unit vector, when we dot a unit vector by itself, we just get one. So this is going to simplify to just be minus d for region 1 times the gradient, which is just going to be d phi dr for region 1, and this is evaluated, this derivative is evaluated at the interface. And then that's going to be my normal component of the current for region 1, and that's going to be equal to the diffusion coefficient in region 2 times d phi dr in region 2 evaluated at the interface. And that's what this line in our interface is saying. It's just saying we're taking the derivative of the flux with respect to r, and then we're evaluating that quantity at whatever this interface radius is. So that's what our interface conditions look like. And because it's an infinite problem, there's no boundary condition. Like you don't have a boundary of an infinite system, but we still have to ensure that we have continuity, that we maintain physical realizability of our flux. And so the governing equations that we had on the last slide combined with these interface conditions is everything that we need mathematically to start solving the problem. And so once we write all this out, the next thing that we do is just try to solve each equation separately and get general equations for each region. So if so this is just writing out what those general equations are. This was for region 1 and that was for region 2. And so if you are looking at an equation like this, then the next thing that we need to do is spell out what the Laplacian operator looks like for this geometry. And I needed to fix my slides. So you guys already have this, but the Laplacian operator in spherical coordinates, looks like 1 over r squared, d by dr of r squared, d, and then we just have another d by dr on the inside. D by dr. And if you have like a little function f here, then you have a little function f here. And so that's what the Laplacian looks like for spherical coordinates. So we rewrite our governing equations in terms of that Laplacian. And then these are the general differential equations that we can find general solutions to. And so if you get a differential equation that looks like this first one or the second one, you don't have to be able to solve that like fully, and that it's totally fine to say I recognize this differential equation and then I'm going to jump to the general form for that differential equation. And so um, I meant to, hold on, let me see if I put it. Okay. I meant to have this right after that slide, but so this is kind of that table that I was talking about that's in our formula sheet. In engineering, you often run into like the same kinds of differential equations pretty often. These are also the differential equations, at least for especially 1D slabs and spheres, that it's like pretty easy, or at least it's possible to solve them analytically. So if we get a differential equation like either of these or even the cylindrical one, we just really need to be able to jump to what's the general solution form, and then we can proceed from there. So in this case, when we have 1D spherical coordinates, the solution or the general solution of this equation is going to either be, it's going to depend on if this quantity here has a plus or a minus sign. So if you have a plus sign, which is what the F plus is, it's saying this is the solution I get if I have a plus sign in my differential equation. Then for the plus sign in between these two terms, it's going to look like a sum of sines and cosines. Oh, and I also have a typo here. That's supposed to be positive. Um, it's just a sum of sines and cosines divided by r if we're in 1D spherical coordinates. And if there's a minus sign in between these two terms, then it's going to look like this F minus solution where we're going to have a sum of exponentials divided by the radius. So like slab and slab and spherical coordinates, these solutions look very similar, with the only real difference being that you pick up a factor of 1 over r when you write these solutions for spherical coordinates. So that's kind of how I help remember them. But in this case, we've got 1D spheres, so these are going to be the general solutions that we jump to. Yeah. Oh yeah, thank you. I think I fixed this on the slides that I uploaded, but then I forgot to upload that PowerPoint to this computer. So while y'all were doing the quizzes, I was trying to put my slides back together. Yeah, thank you for pointing that out. That should be an R as well. So that's just helping us understand why we jump to here, right? So all I'm doing is recognizing that for region 1, this is what my solution looks like. And for region 2, this is what my solution looks like. And now that we know what our general solutions are for region 1 and 2, we can hopefully simplify those equations a little bit. For example, in region 1, because the radius can go from 0 all the way up to that interface, we could have bad things happen at r equals 0 depending on the form of these equations. And just like we saw last time for the 1D sphere problem, if we look at the sine of x over x, it kind of looks almost just like a nice kind of trig function. Whereas if we look at the cosine of x over x, we get this kind of weird thing that spikes to infinity at x equals or r equals 0. So because of the nature of this second part of the first equation, if we let r go to 0, then this cosine over r term could blow up to infinity. So if we don't want our solution to blow up to infinity, that means that C2 has to be 0. So because of physical realizability, we can knock out this part of the solution to region 1, and that means that our region 1 equation simplifies by quite a bit. And so that's where we can have problems in region 1 is at 0. For region 2, with these exponential terms, we don't have any problems at the interface, but we do have problems at infinity. Because if I were to plug in r equals infinity here, if I were to plug in r equals infinity into equation 2, which of these terms would go to infinity as r goes to infinity? The C3 term or the C4 term? Because we've got an exponential that's just positive here, whereas we've got an exponential that's negative here. So if I think about like an exponential equation, um, as if it's a positive exponential, it's going to look like that. And if it's a negative exponential, it's going to look like that. So that's a positive exponential. That's a negative exponential. So if this is r and we let r go to infinity, this C3 term could blow up to infinity because we've got a positive exponential that could go up to infinity. So we have to make C3 be 0 so that this term that could go to infinity doesn't. So in that sense, the C4 part is going to be the only one that we care about that we keep in region 2 to make sure that we have a physically realizable solution. So instead of having to find 4 constants, we've used physical realizability to mean that we only have to find 2. And we have 2 constants, but we also have 2 more equations that we can use to find those constants, which is the interface conditions. Continuity of flux is one, continuity of the normal component of the current is the other one that we can use to find those constants. And in general, if you have for every interface, you'll have 2 constants that you have to solve for. So in a 2-region problem, you have 1 interface, so that means you have 2 constants that you need to solve for. If it was a 3-region problem, there would be 2 interfaces, and therefore you would have 4 constants that you need to find. So we've found these are the simplified forms of our region 1 flux and our region 2 flux, and we need to make them match at the interface. So we're going to do continuity of the flux at the interface, where this is our governing equation. We're writing the form for phi1 and we're writing the form for phi2, and then we're evaluating it at that interface. So in for r, little r, we're replacing it with the interface radius. And we're also plugging that interface radius in here for this little r. That ends up meaning, if we look at both sides, that these r interfaces cancel. And then if we get everything on one side, then this is going to be like our equation 1. Where all we're doing from here is just moving the C4 term to the other side. So this is the first equation that we will use to find these constants. And the next equation is going to come from using continuity of the normal component of the current. So again, this is the definition of normal component of the current continuity. And now we need to take the derivative of these 2 functions with respect to r and plug them in. So if I look at what I have on the left side, which is based on my region 1 solution, so if this is my region 1, that's what I'm doing here. And if this is my region 2, that's what I'm doing here. And I'm just kind of showing what the steps would be, that I'm taking the derivative of the region 1 flux with respect to r and evaluating that at the interface. And so because this is a sine function over r, when I take the derivative, I have to do quotient rule, that I'm taking the derivative of 2 things being divided by each other. So just like as an aside, this is how I remember how I learned quotient rule, is that if I have some function that's got like a part on the top that I call the high function and a part on the bottom that I call the low function, then the derivative, if I have a function that's got a quotient, then the quotient rule says the derivative of this function is I do the low function times the derivative of the high function minus the high function times the derivative of the low function, and then all divided by the low function squared. So that's just helping us remember what quotient rule looks like. And that's where these derivatives are coming from. In this case, my low function is little r. And so that's why in the denominator, I basically have that r squared, but then I've evaluated at the interface. And then in the top, I'm basically just doing the derivative of the high function times the low minus the high function times the derivative of the low function. And so in both of these cases, when I do the derivative of the low function, which is r, the derivative of r with respect to itself is 1. So that's why this term with a minus is basically just looking like the sine part. And similar story here, except I've simplified this by factoring. But all that's going on here is that we're just doing quotient rule on these two functions to get these expressions for the derivatives, and then we're evaluating them at the interface. And so these two things are equal to each other, right? This and this are equal. So if we set them equal to each other and then we rearrange and again, the interface radius squared is going to appear on the bottom, and this doesn't need a superscript. I've got the same interface radius on the bottom, so those would cancel. And then I could rearrange to make my equation look like this. And the whole reason that I'm rearranging like this is for the solution process that I would go through to solve for those coefficients. So I've got something that's a multiple of C4 and something that's a multiple of C1, and this is all set equal to 0. So that's my two equations that I would use to solve for these two constants. So this is what we found for region 1. This is what we found for region 2. And now, by the nature of these equations, we've got homogeneous linear equations that are in terms of these constants C1 and C4. They're homogeneous because the right-hand side is equal to 0. And I've written it in this form so that we could hopefully see how these two equations could fit into a matrix, where we're kind of setting it up such that such that this part is my coefficient matrix, and then it's multiplied by my column vector of solutions that I'm trying to solve for. And so symbolically, this looks like a coefficient 2 by 2 matrix multiplied by a column vector that I'm trying to solve for that has two elements, and that's equal to the 0 vector also with two elements. So if we're trying to solve these constants and we have a linear algebra problem like this, then this system is going to have non-trivial solutions if the determinant of this coefficient matrix is equal to 0. So to figure out what these constants are, we need to take the coefficient matrix, take the determinant, set that determinant equal to 0. So that would be the next step. We're going to take the determinant of that resulting 2 by 2 matrix. And if y'all have a 2 by 2 matrix, do y'all know what the form of the determinant looks like? Just as an aside, if I had 1, 2, 3, 4, and then I wanted to take the determinant of that, what would it look like? Perfect, right? She said 1 times 4 minus 3 times 2. So in other words, and that's exactly right. So it'd be 4 minus 6, which would be -2. So all you're doing when you're taking the determinant of a 2 by 2 is you're kind of like multiplying these guys across, and you're multiplying those guys across, but you add a negative when you do the second part. So, and this is also just a 2 by 2 matrix. Oh, yeah. Mhm. Um, Non-trivial means non-zero. So if we plugged in C1 equals 0 and C4 equals 0, technically that would be a solution, but we're not interested in the non-trivial solution. Yeah, so it's just the solution that's not 0. Good question. Thank you. So this is just a 2 by 2 matrix, and we can do the exact same thing. We're going to do this. We're going to multiply the diagonals. So these two terms will get multiplied together. So I'll have like sine of the buckling in region 1 times that interface multiplied by the diffusion coefficient in region 2 times the exponential of negative B effective for region 2 times that interface radius. Oops, my parenthesis looks bad. And then times the B effective for region 2 times that interface radius plus 1. That's the first term when I get when just multiplying these two guys together. And then the next term, I'm multiplying these two guys together, but I pick up a minus sign when I do that. And so if I were to multiply these two terms together, this guy already has a minus sign in front. So those two minus signs are basically going to cancel each other out. And so then I'm going to have plus, I'm going to write this term first. So I have the diffusion coefficient for region 1 times C. Sorry, this is a typo. This C1 should not be there. Apologies for that. The whole point of putting it in this form is that we're kind of like factoring out those C1s and C4s. So just make sure you get rid of that. Otherwise, that'll confuse you. So there's no C1 here. But I've got this BM1 times that interface times the cosine of BM for region 1 times the interface radius minus that sine function of BM1 times that radius of the interface. And that whole thing is being multiplied by this exponential. By the exponential of negative B effective for region 2 times that interface. And that whole thing is equal to 0. So if we look at this equation, we've kind of got some common terms in that both of them contain this exponential. So if we were to divide both sides by that exponential, it's just going to drop out of the equation. And then also, um, if we divide by the sine, notice that both equations also contain this term, the sine of BM1 times the interface. So if we divide that on both sides, then the sines are going to cancel on both of these places. And on this cosine term, we're going to have a cosine of that quantity divided by the sine of that quantity, and cosine over sine gives you cotangent. So that's how we get to here. We're basically just dividing out those two terms, and then we're also rearranging the expression. Um, and so this thing in the box, this is what we would call the criticality condition. This is the criticality condition. And the point of this condition is that it kind of tells us, notice that the left side contains material buckling, which is like a material property, and it contains the radius of that interface, which is a geometric property. And the cotangent function is like got those crazy like things that look like that. So it's a very quickly changing function. And then on the right-hand side, we've got the diffusion coefficients, which are also material properties. That's related to like the total cross-section or the transport cross-section, as well as B effective, which is another material property, and the radius, well, which is a geometric property. So the right side is like a slowly varying function of geometric and material properties, and the left side is a quickly varying function of geometry and material properties. And in practice, what we would do is like if we knew what our materials were, then we could work out what all those material properties are, and then the only unknown would be the radius. And then numerically, we would solve this equation to figure out what value of that radius gave us made both sides of this equation equal. And if you were to find some combination of geometric properties and material properties that you could plug into this equation to get the left side equals the right side, then you would have found all of the critical you would have found what you need to make that system critical. You would have found your combination of geometry and materials that gives you a critical reactor. And then that is what would allow you to determine what all of these properties are, what your BMs are, what your diffusion coefficients are, and what the radius of the interface is. And once I know what all of those numbers are, then I could jump back to these definitions. And if I knew what these numbers were, I could plug them into equation one, I could plug them into equation two, and then I could solve for those constants. So this is basically what we did. We would take this criticality equation, and this was from the last time I taught this. We would solve this equation numerically to find those combinations that gave us the left-hand side equals the right side. And then once we knew what those coefficients were, we could like take that first equation and we could get C4 in terms of C1. Um, and so once we do that, then we can write our scalar flux for this multi-region problem kind of like a piecewise function where this is what that function looks like from 0 to that radius interface, and then this is what the function looks like going from the interface radius all the way up to infinity. And and we're writing it all in terms of C1 because like region 1 is going to contain C1 as the constant. Region 2 contains C4 as the constant, but like we're showing right here, we can write C4 in terms of C1 and these other multipliers. So if I'm that's kind of how we get just one constant by itself is here we're rewriting the C4 in terms of C1. That's also why we're picking up this exponential of B effective for region 2 times that interface radius. That's where this part is coming from. It's coming from putting this in for C4 and then lumping the functional part of the exponential with this constant part of the exponential. And that's also why we're picking up the sign term in region for the solution in region 2. And so that's what that solution would look like. And then the only thing you would have left to do is to find C1. And in this case, we could find C1 by knowing something about the system. Like if we knew the reactor power, then we could integrate over the power producing region, which would just be region 1. And we could relate we could relate the power and that integrated quantity to C1 to get C1 in terms of that reactor power. So that's the example of doing multi-region diffusion. And so in general, multi-region diffusion is kind of just like one-region diffusion, except you have the interface conditions that you have to use to match the solution from one region to another. So in general, when you're doing multi-region diffusion, that's the process that we want to go through. And so from there, I just wanted to talk a little bit more about kind of properties of two region systems, specifically the properties of reflectors. Um, so this is just kind of like illustrating why we like reflectors in nuclear engineering. So like we're thinking about comparing the design of two different critical reactors that are made of the same fuel. And so the first reactor would be a bare reactor, so like a just a one chunk of spherical fuel surrounded by vacuum, and it has a certain radius R1. And then we have another reactor that's got an inner core region with a radius R2, and then it's surrounded by a reflector. And so the question is about the radii here. How do we think these two radii would compare? Do we think that R1 would be bigger or R2 would be bigger? They're both critical. They have the same fuel, but one is a bare reactor that is critical, and the other one is a interior core that's critical and is surrounded by a reflector. Which one's going to be bigger? You have a 50% chance of getting it right. Yeah, perfect. R1 It's almost like, so we'll say definitely that R1 is going to be bigger than R2. And if we think about the bare reactor, it is critical with all of the neutrons leaking out of it once they get to the outside, whereas the second reactor has a reflector surrounding it. So if that second reactor is critical still, but it has that reflector is going to bounce some neutrons back in that would have otherwise leaked. So the addition of a reflector allows you to make your reactor core smaller. So that's basically what we want to say here is that the addition of the reflector reduces your leakage and it allows for smaller core volumes. Um, so in that sense, I guess with a can do, it's a different, I guess it's similar, but it's different in that it's more about the moderating properties of the fact that can do's use instead of regular water, they use heavy water, so it's D2O instead of H2O. And deuterium is a very good scatterer. Like it's the best moderating material that you can use. And that is what allows the CANDU reactors to operate with natural uranium. It's like you're trading off the enrichment with using a way more expensive moderator. So yeah. Um, and so when we talk about the kind of difference between a reflected configuration and a non-reflected configuration, the difference in those radii has a name that's called the reflector savings. And we use a little symbol like a delta for the reflector savings. And the definition of delta is just the difference between the radius of a bare reactor minus the radius of the reflected reactor. So, like just like we were saying up here, the bare radius is going to be larger than the reflected radius. And if we knew what those radii were and we subtracted them, that would give us the reflector savings. Both of the radii are going to have units of length. So that means that the reflector savings also has units of length. And it basically tells you about how much your core dimensions get reduced by the fact that you've added a reflector, which reduces the leakage out of your system, which makes it easier to get a critical configuration with less material. So the fact that they reduce leakage, the fact that they allow for a smaller core volume are two reasons why we like to add reflectors. And there's other reasons that we like to add reflectors too. Um, if we wanted to make those two reactors have the same radius, we could, and then in that second reactor, we could actually lower the enrichment a little bit, which would make our fuel cheaper. So another way that the reflector is good is that it allows you to reduce the fissile fuel enrichment. Like in terms of the atom percent of U-235. Um, so you could reduce the enrichment and still get a critical configuration by adding a reflector. Um, when we talk about reflection, it's like the neutrons are bouncing off of that material. So in that sense, reflection is a scattering reaction. And in scattering reactions, the neutrons can lose energy as well. And when neutrons lose energy, it becomes more likely that they can cause a fission. So it increases their chance to cause fission. So like if we didn't have that reflector there near the outside boundary of our fuel, those neutrons would just leak out. But with the reflector there, they have a chance to bounce back in. And in that bounce, they can lose some energy, which makes them more likely to cause a fission with that outer material in the fuel itself. And so that kind of flattens out the flux profile because instead of it just being a big value in the center and then dropping off kind of pretty fast as you get to the outside, it raises the flux along the outer periphery of the core, which will flatten the flux profile. And this picture right here is a good picture to keep in mind when you're thinking about the difference between so the first one is a bare core surrounded by vacuum. And so the flux peaks at the center of the reactor and then it drops to zero once you get to the vacuum, because that's what the vacuum boundary condition does. If instead we took that same core and we surrounded it by a reflector, then notice that the radius of the core becomes smaller because we can make a smaller radius. We can make the reactor critical with a smaller radius. And also the addition of this reflector causes a little bump in the scalar flux because of those neutrons scattering back into the system. Um, so the consequence of this is that if we compare the average power, if we relate the flux to the power, then the flux and the power are proportional. So increasing the flux profile in the outer core region increases the overall average power of the reactor without doing much to increase like the peak flux and the peak temperature. So it allows us to it allows us to, yeah, uh, that increased flux in the fuel near the reflector increases the core's average power without changing the maximum power density. And that's also good. In a big reactor, the flux profile is really important because the flux will influence how fast the fuel burns up. And so if your flux is really hot in the middle and very small on the outside, then that fuel on the inside of your reactor is going to get used up really quickly. And you're going to have a lot of fuel on the outside that doesn't get used. So adding a reflector allows you to get more use of that outer fuel, which both it makes your reactor more economical, but it also makes things just better from like pretty much every perspective. Like from a thermal perspective, it's better, and from like a operational perspective, it's better too, because it means that you don't have to switch your fuel around as much. And so that's the last thing I wanted to say about one group diffusion. And that is where chapter 3 ends. One group diffusion is a very useful model, especially if it's a large homogeneous reactor. It does a pretty good job of predicting things. If you get away from that, it becomes less reliable, but it's still a very good framework to understand and think about specifically how do neutrons spatially distribute themselves in different kinds of reactors. Like anytime I've done calculations involving, I'm working on the molten salt reactor project. Our reactor core is a big cylindrical chunk of graphite. We pretty much always use that flux profile for a cylinder where you've got a where you got a radial Bessel function and you've got an axial cosine distribution. If it's a cylindrical reactor and you're trying to model it using one group diffusion, results are fairly common, especially from like a thermal hydraulics perspective. So yeah, this model is pretty useful, but it has a lot of inaccuracies because of the fact that we've used Fick's law, which is a approximation. Um, the other thing about one group diffusion that is not very good is that effectively with assuming one energy group, we're also assuming if all of the neutrons have the same kinetic energy, that means they also all have the same speed, even though so it's like that V in the equation is like an average speed. In reality, neutrons have a variety of energies within a reactor. There's an energy distribution that the neutrons have, and so a real reactor has that energy distribution, and that's something that we want to be aware of and something that we are going to talk about next. And that's basically the entire idea behind chapter 4 is talking about energy dependence. And so we're going to get into that in just a sec. I just had a couple of odds and ends that I wanted to talk about first. These are a couple slides that I've been meaning to get to, but I kept running out of time. Um, There is these things called ENDFs, which are evaluated nuclear data files. If you're designing a reactor, you have many different materials, every isotope on the chart of the nuclides you could choose from, and all of these different isotopes have different nuclear properties. So if you're trying to design a reactor, you need nuclear data, and the ENDF is where you can get it. Um, there's lots of different places that you can get this information from. I would recommend a tool called Janus. And so I was just going to quickly show you how you can find nuclear data on Janus. So if you go to Google and you type Janus, the first thing that's going to come up is Janus Joplin. So you always have to type Janus nuclear, and then you'll get the Nuclear Energy Agency database. There's two ways that you can do this. You can download like a little client, or you could just look at it all on the web. We're probably going to look at it on the web, so that's how I would go about it. At least, yeah, if you're looking at this for the first time, you're probably just going to use the web version, but um, this is not how it usually looks. So we're going to search within E&D. I've never seen this before. Okay. So within ENDF, you can talk about what is your incident particle. So if we're talking about cross sections, that's going to be based on the incident. Here, let me zoom in on this a little bit. We're going to look at incident neutron data. There's all kinds of different libraries that you can pick. Many different libraries exist. The one that I always use is just the newest version of the ENDF. Um, and then I'm going to do search. And so once you do that, it you're going to get a lot of different kinds of cross sections. So like MT1 is the total cross section, MT2 is the elastic cross section. If I'm sorry, this does not look like the way that it looked like the last time that I looked on here, so that's why I'm kind of have this weird look on my face. If we go to total and then we look at those selected results, awesome. Okay, well then let me see if I still have Janice on here. Awesome. This lecture is going wonderfully. I don't know why it's doing that. Ah, that's wild. Okay. This is not what I was hoping to see. Uh, if you need to look up data, this is the way to do it, but for some reason this page is not the way that it's looked before. I think what I'll do is I'm gonna go back to my office, get the actual web version of Janus, and then I'll upload a short video that shows how you could look up data in Janus if you needed to. I think there were a couple problems, like in problem set 2, where it asked you to look up data. So I wanted to walk you through how to do that, but I am running into unforeseen issues. So I'm gonna skip on that demonstration until I can get that for you from my office. Um, the other aside that I wanted to talk about is decay chains. Very common kind of style of nuclear engineering problem that I've seen in like almost every nuclear engineering class is talking about decay chains. So like this is an example. Excuse me. This is an example of a decay chain where you have nuclide X decaying to produce nuclide Y, which is decaying to produce nuclide Z. And the nuclide Z is a stable nuclide, so it doesn't decay once it becomes Z. And lambda is the symbol that we use for the decay constant of a nuclide. Every different radioisotope has a different decay constant, which has units of inverse seconds. So it kind of tells you about the probability per unit decay of a given isotope. And this is related to the half-life. If you know the decay constant, then the half-life is ln of 2 over lambda. And you would have a different one for every isotope. And this is comes from the fact that these equations basically look like standard what become exponential equations when you set them up. And the way that these equations are set up is just by doing conservation. Each of these are the governing differential equations for the nuclides in this decay chain, where in this case, Ni of T is the number of atoms. You can write it as either a number of atoms or on a density basis, but in this case, this is the number of atoms of nuclide I. And so what each of these equations says is rate of change of that nuclide equals all the ways that I might gain that nuclide minus all the ways that I might lose the nuclide. And here we're allowing for a production rate in units of atoms per second for each nuclide present. So the way that these nuclides are gaining is by this production term adding them into the system. And then as these nuclides form, they will decay. So for nuclide X, it's gained because of that production rate, and it's lost every time it decays. So there's a minus sign because this is a loss term, and if I do the decay constant for that nuclide multiplied by the amount of that nuclide, that's what gives me the activity, which is what tells me about the number of decays per second, or the number of atoms per second that are undergoing decay. So that's what my governing differential equation would look like for nuclide X. For nuclide Y, it looks the same. It's change rate equals gain rates minus loss rates. We have a production term for nuclide Y, but also because nuclide Y is in the middle of this decay chain, every single time X decays, it produces Y. So Y also has an additional gain term that looks like the loss term from nuclide X. Every time X decays, it produces a Y, so the lambda X times the number of X is one of the gain terms in my Y decay, in my equation for isotope Y. And then Y also decays, so it has a loss term based on its own decay. And then when I get to nuclide Z, it has a gain term if there's a production rate, and it also has a gain term because of the fact that every time Y decays, it produces Z, and Z is stable, so it doesn't itself decay, so there's no minus signs for any decays from Z. So each of these equations is just a conservation statement. And if you know these equations and you also know these initial conditions, these would be my initial conditions, then you could solve each of these equations for the amount of that nuclide as a function of time. Um, and so, yeah, I think we've hopefully seen that before. If we haven't seen that before, that's a good refresher. And you've had a couple examples that talked about these decay chains. So I wanted to make sure I took a couple minutes to just explain how you would set these equations up, and then you can solve them once you know how to set it up. Solving them is the next thing that we could do, and that's what those problem set questions hopefully got us to practice. So yeah, that fully concludes everything before chapter 4. And then I just wanted to like kind of give us a brief intro to multi-group diffusion, where we're starting to think about the energy dependence of the neutrons in our reactor. With multi-groups, we kind of look at we'll kind of break that energy distribution up into chunks, and we'll have different ranges over which we consider neutrons. And if we have neutrons split up into multiple groups, then within each energy group, we can look at all the production and losses for that group, and then we can start writing conservation statements for each separate group. And then yeah. If the number of groups gets large enough, then we can just characterize each group with its own material properties that are like averaged over the energy range for that group. And the easiest starting point is just to consider two groups, a fast group and a thermal group. So kind of thinking back about why we care about energy dependence, if this came from Janus for uranium-235, and it shows the total cross-section, the fission cross-section, and the capture cross-section. And notice that yeah, so notice that these cross sections are heavily dependent on the energy of the neutron, which is what the x-axis is. And so because the energy of the neutron is depending on the cross section, that means that fission, for example, is way more likely if the energy of the neutron is lower, and that means that the reaction rate density is going to be higher if neutrons at low energies are contributing to it. So the energy of the neutrons impacts what our reaction rate density is, which affects our power and our temperatures and things like that. So this energy dependence is very important. Um, and in general, the reactors that we have in the United States and most power reactors are thermal reactors, which means they're mostly powered by neutrons of thermal energies that are causing fission. And in homework one, there was a cool example that got you thinking about what that thermal energy would be for a neutron in thermal equilibrium with its surroundings. And if you did that homework problem, you saw that the thermal neutron energy is about 0.025 eV. So like if I'm looking on this energy scale, this 10 to the 0 means 1, this means 0 0.1, this means 0 0.01. So if we're at 0.002, we're at kind of somewhere in between these two ranges. So like if I just kind of draw a demarcation line vertically up at 0.01, sorry, at 0.1, then this range is what I would consider my thermal range. Fission, the neutrons that come out of fission come out fast. So we'll set 10 to the 5 as just kind of like an arbitrary marker where we would have fast neutrons. And then technically in this middle region, this would be what we call the intermediate range. So I know before I said we would look at two groups. Technically, this is three groups. And it's kind of arbitrary where you set that demarcation line if you just have two groups. That's why it's kind of better to use three. And that's just kind of like where we might set those ranges. Um, and so yeah, thermal neutrons are where we get the most likelihood of having a fission event happen. And fast neutrons are important too, though, and that has to do with the fission spectrum. This is also something that we talked about in lecture one. So this red curve right here is my fission spectrum. That chi of E is my fission spectrum. It's a probability density function. So it tells you about probability per unit energy that a neutron is born from fission with some energy E. And this was the plot that I showed in the first lecture, but if we switch that plot over to a log scale, and I know that this says probability, but this is the same thing. So this is a probability density, and this probability density also has units of like inverse energy. So this red line and this blue, those are the same graphs. This is just putting it on a log scale. And putting on a log scale helps us to more easily see that this peak that's around 0.35, which is the same peak here, occurs around a neutron energy of about 1 MeV. So what that means, the fact that this distribution peaks at 1 MeV means that if neutrons come out of fission, they can have any energy. They can have energy anywhere within this range, but it's much more likely that they come out with an energy around 1 MeV. And as a result of that, that means most neutrons are born in what we would call the fast range. So when a fission happens, the neutrons that come out of it are very fast. But if we want to make those neutrons cause a new fission, they need to be thermal. They need to be slowed down. And so, like, if our neutrons are born here and we need some way to slow them down, we need to slow the fast neutrons down so that they make it to the thermal range. And the way that we do that is with materials that are good at scattering, because scattering reactions are the way that a neutron can have a collision with something and not be absorbed by it, but bounce off of it to lower its energy. Um, and I guess just kind of continuing that thought, if you have neutrons in your reactor, they could scatter off a lot of different things. Like they could scatter off uranium, they could scatter off iron, they could scatter off any nuclide that's present within your reactor. And so a neutron's very small. It's like it's about the same size as a proton. And so if you imagine like a pebble and a basketball, where the pebble is kind of like your neutron and the basketball is like your uranium-235, if the pebble hits the basketball, just like in a simple scattering reactions are just like collision reactions, basically. So if that neutron hits that, if that pebble hits that basketball, the neutron isn't really going to lose a whole lot of energy in that collision. Like the when the neutron hits the basketball basically isn't going to move. So not very much energy would be transferred in that kind of collision. But if we had a pebble and another pebble, and we shot the pebble at the other pebble, then those things would bounce off of each other. The pebble that was stationary would gain quite a bit of kinetic energy, which would have came from the first one. So in that example, the basketball is kind of like uranium-235 or iron or some kind of large heavy nucleus. And the pebble is something that's comparable to the size of the neutron. So, like hydrogen is just a proton. So, hydrogen is a very small nuclei. If a neutron hits hydrogen, it's very likely to scatter off of it and lose quite a bit of its energy in that scattering reaction with something that's comparable to its size. And so that's why scattering materials, good moderators, tend to have a low atomic number. Like you see hydrogen because of water, you see carbon because of graphite is made out of carbon, which is also relatively low on the periodic table. And so, yeah, it's the size of the particle that the neutron is colliding with, which influences how likely it is to have a scattering reaction. Um, there's also quantum mechanical effects as well, because, for example, hydrogen and deuterium is just hydrogen, but with an extra neutron. And so when hydrogen absorbs an extra neutron and becomes deuterium, it fills up deuterium's nuclear shell. And that means that when another neutron interacts with deuterium, it's very unlikely that that neutron could be absorbed within the deuterium. The deuterium is a very good scatterer and basically doesn't absorb, whereas hydrogen has a higher chance of causing an absorption. And that's why deuterium heavy water is like the best moderator that you can get, because it has the same similar scattering properties to hydrogen, but it's much less likely to make an absorption happen. So from like a neutron economy perspective, it's much less likely that stuff gets absorbed within deuterium than it would for hydrogen, which allows you to make critical reactors with much less enrichment. And that's what the CANDU reactors do. They use deuterium heavy water as a moderator, and that as a result allows them to have basically like natural uranium enrichment in those reactors. And so that is everything that I wanted to say today. So if y'all have any questions, please let me know. And if not, thank y'all for your time, and hope you guys have a good rest of your day. Have a good weekend, and I'll see y'all in class on Monday, where we'll pick up and continue with chapter 4, talking more about energy dependence and start talking about multi-group diffusion.